In this video, we're going to get into material from Chapter 1. I'm actually going to break Chapter 1 into two parts, so this is going to be the first part. We'll be covering units and measurements. As scientists and engineers, you're going to make measurements all the time. Some of the things you're going to measure are weight, time, distance, and volume. You're also going to spend a lot of time collaborating and exchanging information with other people. With different people making different measurements, a problem arises. What I'm showing here are different ways of reporting the same measurement. They're known as units. If you're trying to collaborate with other people and everybody's using different units, it becomes difficult to compare results. In order to address this situation, there's an international system of units. This is often known as SI units. Now, why it's SI units and not IS units is because SI is an abbreviation from the French pronunciation. There are three primary quantities we're going to concern ourselves with this semester. For time, the standard is seconds, length or distance, meters, and mass should be kilograms. These are often known as the MKS SI units. We will be using these SI units this semester. Now, this doesn't mean that every time you report a quantity it has to be in terms of meters, kilograms, or seconds. For example, sometimes a long distance using meters is not convenient, so you would use a multiple of that, like kilometers. Or if you're measuring mass and you have a very small quantity, you would report kilograms or hours for time. All of those are multiples of their base SI unit. When you're using some multiple of these base units, it's important to understand the common prefixes that go along with those. These are just a few that you will be expected to know this semester. Most people have seen these before, especially if you've had science classes. For example, micro is 10 to the minus 6, or it's the unit divided by a million. If you're into computers, you'll recognize megabytes. That's 1,000,000 bytes. Of course, kilometers are used a lot. That's just 1,000 meters. So if you're not familiar with these, you'll definitely want to get to know these better. The book, our textbook actually has a more complete list of common prefixes, and it'll be handy throughout the semester, especially on homework. There's some questions that you could use that for. Of course, you can always Google them as well. When I teach this class, I often see students who have the habit of reporting a number without any unit. I actually understand this. We haven't been trained to do that. Most of our math classes only cared about the number, and the unit was just a secondary thought. In physics, and actually science and engineering in general, units are required. They're necessary, but it's important to understand why. So let's address this question. Why should I always include units when reporting a result? Well, here's just one example to emphasize my point. Imagine you receive a message that says, "Congratulations, you've earned 1,000. How am I supposed to interpret that? Is that a good thing? Have I earned $1,000? Is it just 1,000 pennies? Either way, that's not necessarily a bad thing, but what if it is less desirable? Like, I've earned 1,000 bags of garbage, or I have to do 1,000 hours of community service. So without the units, there's no meaning to the number. This is why you need to report a unit, because every measurement in this course should represent a real quantity that's been measured. Here's another example. If you reported that the length of the table is 3. Again, what does that mean? Is it 3 feet? That seems reasonable, but maybe it's 3 meters. Well, that would be a long table, but there are tables that are long, so maybe that's what we need. So again, without the units, it just doesn't mean anything, so you should get in the habit of using them. Later in the video, I'll show you that there's another reason, and specifically, if you want a good grade in this class, you should pay attention to that reason. So we'll get to that a little later. Because all school has been suspended for the rest of the year, I've been spending a lot of time with my kids teaching them math and other subjects. This is a type of problem I've seen with my daughter who's in 5th grade. I thought it was interesting because it's totally applicable to what we're doing right now. John walked a distance of 242 feet. How far did he walk in meters? Well, addressing the unit issue, this would be a conversion to SI units. What I found interesting is the way they teach it to my 5th grade daughter, in my opinion, was actually quite confusing. It was sort of silly in a way, and it made it more complicated than it needed to be. But the problem is my daughter doesn't understand algebra yet, so it turns out that if you understand algebra, there's actually a pretty easy way of doing this. It actually utilizes the power of 1. So let me explain what I mean by power of 1. Now I will warn you, I'm going to start handwriting. This is going to be useful for this class because we've got a lot of handwriting ahead of us. So I bought a drawing tablet. If you don't know what that is, it's just a black surface, and I actually can't see what I'm drawing. I have to watch the computer. It's kind of confusing and it's not very intuitive, so I need to get used to it. This is actually the first time I'm going to try it out, so be warned, my handwriting is already not awesome, but this just makes it that much worse. I'll do my best to keep it legible, but I can't promise anything. So here we go. What do I mean by power of 1? Well, it starts with just a simple equality. If A is equal to B, we know from algebra that I can do anything to either side as long as I do the same thing to either side. So what I get from that is that A divided by B is equal to 1. Let's try that again. 1. There we go. Okay, that might not seem like it's very useful, but before I explain that, let me just show you something else. I can also, skipping a little bit of the algebra, claim that B over A is equal to 1. So why is that useful? Well, here's an example. 11.74 multiplied by 1 is equal to 11.74. Okay, here's another one. 0.83. We'll do a different notation. Times 1 is equal to 0.83. All right, now this isn't shocking anybody. This is basic mathematics. Any number multiplied by 1 is unchanged. It's just the original number. So how is that useful in terms of units? Here's some relationships between different units. So how is this useful? It says that 1 foot is equal to 0.305 meters. Well, I can take that equality and I can rewrite it as 1 foot divided by 0.305 meters is equal to 1. I could also say 0.305 meters divided by 1 foot is equal to 1. Again, I warned you about my handwriting. Sorry, I'm doing the best I can. Okay, that is actually useful for our problem. Let's go to that again. So I know that John walked a distance of 242 feet. So I'm going to write here 242 feet. And I want to get rid of feet and replace that with meters. So I can multiply this whole value by 1, which doesn't have any effect. So as long as I'm multiplying it by something that equals 1, nothing actually changes. A useful factor would be something that has meters and feet in it. And I specifically want to get rid of feet and replace it with meters. So I need something with meters on the top, 0.305 meters, and something on the bottom with feet, That way feet and feet cancel out. This is just a power or a factor of 1. So there is no real change, and I can figure out the result. That is equal to 73.81 meters now. Okay, this thing right there, because it was used to simply convert my units but not change the quantity, this is called a conversion factor. Another issue that we should be aware of is it really appropriate to report 4 digits there? We'll talk about this more later, but the answer would be no. In this case, I should only report 3. I'll explain more about that later. But anyway, this is the power of 1 in terms of unit conversion. If you've had a chemistry course, they teach you something similar to this. The structure might look a little bit different, but it's essentially all the same. This is actually, in my mind, easier than what I had to teach my 5-year-old daughter because it was difficult for her to understand the algebra. What if later I wanted to take this value and convert it to inches? Well, 73.81 meters. Now I want to get rid of meters and use inches. So I'm going to use a conversion factor that has inches in the top. And meters in the bottom. Meters cancels out, and I'm left with 2,900, and I'll round that off to 6 inches. Okay, hopefully that gives you an example of what we call unit conversion. If you already are familiar with this and it's easy for you, that's great. That's a great thing. But if you haven't done it before, we're going to be doing this a lot this semester. And I do mean a lot, so you really need to understand it now. Put all your effort into understanding this if you haven't seen it before. Okay, let's go to a different example. John drove in his car at 45 miles per hour. By the way, this is really saying miles per, which is a division, hour. So be familiar with the P, the per, it's a division symbol. So what is 45 miles per hour in kilometers per hour? Actually, let's write it like this, miles per hour. I need to replace miles with kilometers, so I need a relationship that has miles and kilometers. It looks like there it is right there. I want to get rid of the miles, so I need to make sure and put that part in the denominator. All right, and the kilometers would go in the numerator. That way the miles cancel out, and then I'm left with 45 divided by 0.621 is 72.5. I'll go ahead and leave it, round it to 5, and I'm left with kilometers per hour. The problem also wants to know the answer in meters per second. So let's tackle that one. Now, to do this, we could either start with the 45 miles per hour again, or we could use our 72.5 kilometers per hour. I'm going to go ahead and use that one. All right, now if you look up in the left, I don't have a relationship for kilometers and meters or hours and seconds, but those are something that you should probably already know. If you're not, then you can look them up, of course, but I'll go ahead and start with that. So I need to get rid of kilometers, so I need that in the bottom, And I know that 1 kilometer, as we discussed in a previous slide, was 1,000 meters. Okay, now I also need to get rid of hours, and that's in the denominator, so I need hours in the numerator, and I happen to know that 1 hour is 60 minutes. That doesn't actually solve my problem because it was seconds, but there's nothing stopping me from stating that 1 minute is 60 seconds. All right, now I have 3 conversion factors here. Let's go through and see if I get what I want. Kilometers and kilometers cancel. Minutes and minutes cancel. And hours cancel. So what I'm left with, let's see. I'm going to highlight this. I'm left with meters and seconds, which is exactly what I want. It's actually a little ugly, so I'm going to write this out again just so I can clearly see it. So 72.5 times 1,000, and meters was left over. And here I have 60 and 60 seconds. Okay, when I plug that into a calculator, I get 20.1 meters per second. There are my 2 results. Let's do one more example. This is an important one, so please pay attention to this one. John needed 9.5 cubic feet of concrete. How much is that in cubic meters? If you're not familiar with cubic, that means essentially something that's been multiplied 3 times. So in this case, it would be 9.5 feet cubed. What I want is cubic meters, so that would be meters cubed. If you look on the left, there is no conversion written for cubic feet. But I can still use the information that's given. So if I have 9.5 feet cubed, I can multiply it by, let's see, I want meters in the top. I want to get rid of feet, so I need meters in the top. 0.305 meters divided by 1 foot. I see a lot of times on an exam where this is all somebody writes down, and so they plug that into a calculator and they get some number, and then they just write meters cubed on it. Okay, that is wrong. Think to yourself, what am I missing? Okay, hopefully you recognize that what you're missing is feet, and feet cubed are not the same thing. But this whole thing is equal to 1. Remember that. And I know that 1 cubed is equal to 1. So all I have to do to give me the right units is cube everything inside this. For the point of demonstration, I'm going to actually write that out. This is another common mistake I see. Right there. Okay, so they get that. Everything looks good. My feet and my feet. All of those are cubes, so they cancel out. So I'll plug that into a calculator and I'll get my answer. But again, hopefully you see what's missing here. If I'm going to cube the whole quantity, I have to cube the whole quantity. So I need to cube my value right there. Now I can plug all of that into a calculator and I get 0.2695 4, I'll just write everything out that I had, meters cubed. All right, now later we'll talk about what is the appropriate way to write this final answer, and it's not going to be that. We'll get into that a little bit later when we talk about sig figs, but that is the correct numerical answer. So try out the problems I have on homework for unit conversions. The biggest mistake I see is when something is squared or cubed. In fact, maybe let's just really quick try what happens if let's, for example, I want, let's just make up a number. Let's say I have 8.37 inches squared, and I want to convert that to centimeters squared. Okay, or you could say square centimeters. So I'm going to go 8.37. I need a conversion factor between inches and centimeters, and it's showing up on the top left. So I need 2.54 centimeters, 1 inch. I got to remember to square that, which, remember, means that I'm really squaring that, and that. 1 squared is 1, so it doesn't really do much, but now I can have inches, oops, sorry, that was inches squared. So now inches squared and inches squared cancels out. So I'm left with 8.37 times 2.54 squared centimeters squared. You can plug that into a calculator and figure out the answer for yourself. One last example on unit conversion. Sometimes there's a good reason to use non-conventional units. Here's an example. Let's say that Sparky the elephant has a mass of about 3,600 kilograms. John has a mass of about 82 kilograms. What's the mass of Sparky in John masses? So for this problem, this is the unit that we're asked to convert to. That's certainly a non-conventional unit, but there are certain times when non-conventional is the most convenient. We're going to do this the same way we did all of the other problems. We know that 1 John mass is equal to 82 kilograms. So this becomes our conversion relationship, and then using the power of 1 we can convert that to a conversion factor. So again, we know 1 John mass is 82 kilograms. Here would be our conversion factor. Following the same steps as before, 3,600 kilograms multiplied by our conversion factor. Our kilograms cancels out. The result is 43.902 John mass. Later, again, we'll talk about appropriate digits to report. In this case, it would be 2. So we'll round that up to 44 John masses. So this is an example of non-conventional units, but there could be a good reason why I care about this. If you grew up in the United States and you're not comfortable or familiar with using metric units, there's some approximate conversions that you should keep in mind to use as a way to quickly assess if an answer makes sense. Here's some of the most common ones that you'll see. The one that I want to focus on the most is this one right here, or this one right here. Okay, let's do this one first. So let's say you're solving a problem and you find that John ran a speed of 30 meters per second. Well, because you're not familiar with meters per second as a unit of speed, you go ahead and circle that as your answer and you move on. Well, it's helpful to just assess whether this makes any sense. If we're talking about a human being running, from the relationship below here, 30 meters per second would be about 60 miles per hour. There's no way a human being is going to run at 60 miles per hour. So clearly there was an error somewhere in your work. This is why having approximate conversions in mind is helpful when it comes to tests or homework, because you can check, does my answer make any sense? All the problems we do should make sense. If you're talking about a car and you find out it's driving at 450 miles per hour, no, unless we're talking about some super crazy car, but in general, no, that's never going to work. So these are ways that you can check your work to see if they actually make sense. This was part 1 of the material from chapter 1. Look for a separate video that contains part 2.